Previously, we have been discussing about differential pulse code modulation, and in the previous lecture, we had discussed the block diagram of a DPCM system, and we also looked at the analysis in terms of what are the inputs and outputs of each of these blocks. And the whole idea is that instead of quantizing the actual signal samples, we want to quantize the difference signal d of k, which is the difference between the actual sample value and the predicted sample value. So the advantage it gives us is that because the difference signal is going to have a smaller peak-to-peak range, considering that the predictor is accurate enough, then quantizing the difference signal would result in a smaller peak-to-peak range, right? Because the difference signal is going to be having a smaller peak-to-peak range. Quantizing the difference signal, which has a smaller peak-to-peak range, means that for a given number of quantization levels, the quantization step size would become smaller. And when the quantization step size is smaller, then the quantization error per sample and the average quantization noise power would also be smaller. And the objective while performing quantization is to keep the quantization error and the quantization noise power to be as small as possible, because the quantization noise or quantization error, once introduced, it cannot be removed because it is irreversible. So differential pulse code modulation addresses that problem, wherein the quantization error can be minimized as compared to the normal pulse code modulation. And to achieve that, what is used in DPCM is a predictor, which is a complex signal processing mechanism that uses some statistical techniques to predict what will be the sample value. And once we have a predictor designed which can predict the samples accurately, then the difference between the actual sample and the predicted sample would be very small. That's the whole idea behind differential pulse code modulation. And we also talked about the input to the predictor. What is the input that goes to the predictor that brings out the predicted value? And we made this analysis in the previous lecture. And from the block diagram, you can see that the predictor input has a feedback from its output, as well as the quantized version of the difference sample added to the predictor's output. And when you simplify that equation, that turns out to be mq cap plus dq is nothing but mq of k. So the input to the predictor is nothing but the quantized version of the actual sample value. So m of k is the actual sample value, mq of k is the quantized version of the actual sample value, which is nothing but the actual sample value plus the quantization error introduced as a result of quantizing this d of k. But because the d of k is having a small peak-to-peak range, the quantization error that has been introduced here is going to be very small. Okay, so what we have here, or what you have seen in the previous class and the diagram that is on your screen here, is the transmitter part of a DPCM system. So this is a DPCM transmitter. Okay, where we quantize the difference signal d of k and we get dq of k, and that dq of k gets transmitted further for processing. Now at the receiver side, the receiver would have to get back the actual sample m of k from this transmitted sample value dq of k. But we know that the quantization error is non-reversible. So once the quantization error is introduced, it cannot be removed. So therefore, the best that we can do is to get back mq of k, the actual sample value, including the quantization error. That is what can be recovered or reconstructed. So the receiver part will have to use dq of k as its input, and using dq of k reconstruct mq of k. And The block diagram of the receiver part can be seen from this in this transmitter part itself, which I will mark with the dotted line. So if you see this part, right, so this part here constitutes the receiver part of a DPCM system. So we'll discuss that in more detail. So the objective of the receiver is to get back MQ of K, the quantized version of the actual sample M of K, from the quantized version of the difference sample, which is DQ of K. And all we have to do to get MQ of K is we need to add this DQ of K with MQ cap of K to get MQ of K. So that would become the receiver part of the DPCM system. So we have the receiver part here. I've just redrawn the components which are in this red, circled in this red dotted line separately here in a neater way. So we have DQ of K coming as input to the DPCM receiver, and we are interested in getting MQ of K. So DQ of K added to the output of the predictor MQ cap of K gives us the quantized version of the actual sample MQ of K, which is what we are interested in reconstructing. So the equation here will be MQ of K is equal to MQ cap of K plus DQ of K. And obviously this MQ of K is what is the desired component that needs to be reconstructed, which is also fed back to the predictor input, because if you notice here, the input to the predictor is MQ of K. All right, so we have this feedback going into the predictor as well. So that's the receiver component of the differential pulse code modulation system. Okay, now we've discussed that DPCM indeed gives us an advantage in terms of reducing the quantization noise power, but the next question we need to answer is how much is the reduction in the quantization noise power. So we know that there is a benefit, that there is an advantage, and we now want to quantify that benefit. We need to say how much is the benefit or how much is the advantage or gain that we're getting by using this DPCM system as compared to the normal pulse code modulation system. So we call that as SNR improvement in DPCM, which we will see now. SNR improvement in DPCM. So basically what we're trying to do now is to quantify how much is the benefit we get by quantizing the difference signal rather than quantizing the actual signal itself. So to do that, let us use some notation. We'll denote VPM, okay, V subscript PM as the peak to peak range of the actual signal and we will denote VPD as the peak to peak range of the difference signal. And obviously the peak to peak range of the difference signal is significantly smaller than the peak to peak range of the actual signal when the predictor is having high accuracy. So we can write that VPD is going to be very much smaller than VPM. So if VPD is smaller than VPM, then for a given number of quantization levels, the quantization step size delta, right, quantization step size delta in DPCM will be smaller by a factor VPM by VPD. So by this ratio, by this factor, the quantization step size will also be smaller. For example, if the peak-to-peak range of the actual signal, let's say it is 16 volt, and the peak-to-peak range of the difference signal, let's say it is 8 volt. Okay, in practice it's much smaller, but just for the simplicity of discussion, we'll assume VPM, let's say 16, and VPD is 8, half of it. That means VPD is smaller by a factor of 2. VPM 16 by 8 will be 2. So if VPD is half the size of VPM, then for a given number of quantization levels, the step size delta would be smaller in DPCM by that same factor of 2. So that factor is given by this ratio VPM by VPD, which is the ratio by which VPD is smaller as compared to VPM. Now that's the factor by which the step size delta is going to be smaller, but the quantization noise power, which we denote as NQ, which is delta square by 12, right? We did this proof earlier. The average quantization noise power is delta square by 12. So in DPCM, if delta is smaller by this factor VPM by VPD, then the quantization noise power will be smaller by the square of this factor, because the quantization noise power is proportional to the square of delta, right? So therefore we can write, therefore NQ will be smaller by a factor VPM by VPD the whole square, right? So that's the factor by which we will get a benefit. The average quantization noise power in differential pulse code modulation will be smaller by a factor VPM by VPD the whole square. So this advantage, this reduction in the quantization noise power that we get is called as the processing gain of DPCM. So this is called as processing gain of DPCM. What we mean is that in order to achieve this smaller delta, we are using additional components in the quantization process, which involves a predictor, which is a complex signal processing tool, and therefore we are introducing additional complexity in the system. By introducing this additional complexity, what is the advantage we are getting? The advantage we are getting is a reduction in the quantization noise power NQ by this factor VPM by VPD the whole square, and we call that as the processing gain of differential pulse code modulation. So that's the advantage we get by using differential pulse code modulation, which is the good thing. But with DPCM, the entire analysis is based on the fact that the predictor is able to accurately predict the samples, and the predictor is designed by using the fact that successive samples have a high degree of correlation. So what we mean by that, the entire idea behind DPCM is that samples which are next to each other have a high degree of correlation, in the sense that their values are almost very close to each other. So if you see each of these adjacent symbols, their values are quite similar. So the predictor is able to predict the next sample value, and using the predicted value we are able to get the difference between the actual and the predicted sample, which is then quantized. But sometimes we may have a situation where some part of the signal, as in this part here, is having a high slope, that means even at a high sampling rate, one sample and the next sample, they have a big difference between them. Their values are not very close to each other. In that case, the predictor will not be able to predict this sample accurately, because the predictor is designed by taking into consideration that adjacent samples are having values which are close to each other. So in such a case, the predictor would predict a value which is not accurate. So therefore, the difference between the actual sample and the predicted sample would become too high. That means the peak-to-peak range of the different signal would increase. And once the peak-to-peak range, that is VPD, increases, that means the gain we get in using DPCM, that would become smaller. So VPD will not be significantly smaller than VPM if the predictor is not able to accurately predict the sample, and that could happen when the signal is having a sharp transition from the highest value to the lowest value, or vice versa. It could be transitioning from the top to the bottom, or from the bottom to the top, like this, right? So in either case, when the signal is having a high slope, the predictor will not be able to predict the next sample accurately, and in that case the different sample would have a high value which would increase its peak-to-peak range, and therefore reduce the processing gain that we possible in differential pulse code modulation. And to understand that, and to design the DPCM system in such a way that this situation is avoided, we need to understand what is the maximum slope that the DPCM system can handle. So for that, we need to analyze what is the maximum slope of the DPCM output. So slope is nothing but dy by dx. Slope equals dy by dx. So on the x-axis we have time, on the y-axis we have the amplitude or voltage. So we want to find out what is the maximum slope that can occur in the DPCM output. And the maximum slope that can occur is when the sample value goes from the highest quantization level to the lowest quantization level. When two successive samples are such that one sample is having a value at the highest quantization level and the next sample is having a value at the lowest quantization level, that would be the maximum change along the y-axis. So that's the y-axis. On the y-axis, the maximum step change that can happen is from the highest quantization level to the lowest quantization level. And the step size on the x-axis, in this case, is fixed, which is equal to the sample period. So that's the time period between two samples. So the time period between two samples is nothing but Ts. So dx is going to be Tx. Dx is equal to Ts, which is equal to 1 by Fs. And the maximum value for dy, dy magnitude maximum, is going to be L minus 1 times delta. Now it can be plus or minus L minus 1 delta, and we are interested in the magnitude. So the plus or minus can be left out. How did we reach this L minus 1 delta? So the maximum change that can happen along the y-axis is from the highest level to the lowest level, or from the lowest level to the highest level, right? Suppose if we consider these three samples where the transition is taking from the highest to the lowest and then from the lowest to the highest again, then the change is, it's going from here to here, which is, that one is delta, that distance is another delta, that's another delta, that's another delta, that's another delta, that's another delta, and that's another delta. If you count these, it gives us a total of 7 deltas. and the number of quantization levels here, L is equal to 8. So when L is equal to 8, the number of transitions, now the number of steps that by which these two samples would differ when the quantized values are transitioning from the highest to the lowest or from the lowest to the highest quantization level, is equal to 7 delta, or in general for any value of L we say L minus 1 times delta. So that's 1, 2, 3, 4, 5, 6, 7, right? So it makes a jump of L minus 1 delta. So the maximum slope is going to be, maximum slope is dy by dx. Maximum is dy is L minus 1 times delta divided by Ts. Dx is Ts, which is nothing but, Ts is 1 by Fs, so Fs L minus 1 delta. So that's the maximum slope that we are going to have on the DPCM output, and this is the maximum slope that it can support. So we want to ensure that this maximum slope is at least the highest slope of the input signal. So if we ensure that this maximum slope is at least, that means greater than or equal to the maximum slope of the input signal, then we can avoid the situation of slope overload in DPCM. So the condition to avoid slope overload is that this Fs L minus 1 times delta should be chosen to be at least the maximum slope of the input signal that we are quantizing, d by dt of m of t, and we want to take the magnitude of that, right? And we'll take the maximum, right? So if this condition is satisfied, then we will be able to avoid slope overload in DPCM. And to understand that, let us take a simple signal, a sinusoidal signal for the input signal. So suppose we say we have a signal m of t, which we will simply say Vm sine 2 pi fmt. So we want to find the slope or the maximum slope of this sinusoidal signal. So d by dt of m of t, so that means we are just going to differentiate this. That will be Vm, the derivative of sine is cosine, so it's cosine 2 pi fmt, and it's with respect to t, so we have to multiply that with 2 pi fm. So we can bring this 2 pi fm to the front, so we'll have it as 2 pi Vm fm cosine 2 pi fmt. And the next thing is we need to find its peak value, which is the maximum magnitude. So d by dt of m of t, the magnitude maximum is nothing but the peak value of this derivative. The derivative is also a sinusoid which has a peak amplitude 2 pi Vm Fm, right? The original signal has a peak amplitude Vm. The derivative has a peak amplitude 2 pi Vm Fm. So the maximum magnitude is simply 2 pi Vm Fm. So we need to choose, we need to satisfy this condition that Fs L minus 1 delta is at least this slope, the peak slope of the input signal m of t. So in other words, we have to choose Fs L minus 1 times delta to be at least 2 pi Vm Fm. And this is for a simple case where the signal is a sinusoid having a single frequency component, right? But if it's a more complex signal, then we'll need to find what is the maximum slope of that signal and correspondingly choose the value of satisfy this condition. So in this equation, the number of quantization levels and the step size delta will remain fixed. That's not going to be changed. So we'll end up getting Fs to be at least, we are going to take L minus 1 and delta to the other side. So that will simply make it Fs should be at least 2 pi Vm Fm by L minus 1 times delta. Right? So that's the condition we need to satisfy. That means we need to ensure that the sampling frequency is high enough that it is greater than this term on the right hand side of this inequality. Okay, so if the sampling frequency is high enough, then we will avoid this situation where two samples are having a big difference between them. Two successive samples are having a big difference between them. So if the sampling rate Fs is even higher, then the samples are going to be much closer to each other. That means there are samples even between them, right? In that case, there will be samples between them as well. So the samples would have values which are similar, or they would be highly correlated, and this problem of the samples being not correlated could be avoided if we increase the value, or if we increase the sampling rate Fs to satisfy this condition. Then the slope overload in differential pulse code modulation could be avoided. The next topic that we are going to discuss is called as delta modulation. And to understand delta modulation, we will begin with our block diagram for differential pulse code modulation. And from that, we will see how delta modulation is different from differential pulse code modulation, and why do we need to do such a change. Okay, in differential modulation, we use a predictor to predict the sample value, including the quantization error, and the difference between the actual sample and the predicted sample is quantized and transmitted. Now, the predictor part is a complex implementation. It involves complex signal processing, and therefore the implementation cost and complexity of the predictor is quite high. In order to avoid this complexity, we want to replace it with something simpler in terms of the implementation complexity and cost. And the idea behind doing this is, if we can increase the sampling rate to a high enough value, then the correlation between the samples will become quite large, and in that case, this predictor can be replaced or modeled as a one sample delay. Rather than having a predictor, which is a complex signal processing implementation, we can have a delay modeling the predictor, and that is possible only when the sampling rate Fs is very high, so that the adjacent samples have very strong correlation between them. So the whole idea is to replace the complex predictor with something much simpler. In this case, that simpler component or block is a delay, and the delay is going to be a one sample delay. So it's a delay by one sample. So that's the only change between the block diagrams of differential pulse code modulation and delta modulation. So what you have here is the block diagram for delta modulation. And in place of the predictor, we have a delay, and basically the delay is modeling the predictor, and that model is a good enough representation when the sampling rate is quite large. So keeping everything else the same, if the input to the delay is mq of k here, what would be the output? It would be a delayed version of the input, and it is going to be a delay by one sample. It is 1 ts, right? Whatever is ts. So it will be delayed by one sample. So the output of the delay would simply be mq of k minus 1. Okay, so that's the only change in terms of the block diagram in comparison with the differential pulse code modulations block diagram for delta modulation. Okay, now we will see how this simplifies our implementation. Using this block diagram, we can write down a few equations now. So the first thing is we can write this d of k in terms of m of k and mq k minus 1, because d of k is the difference between the sample mk and the previous sample mk minus 1 or mqk minus 1, which is including the quantization error, right? So let's write down some equations here. So from this block diagram we can write d of k is equal to m of k minus mq of k minus 1. But what is mq of k itself? If we go back one step, okay, when the input is mq of k, the output is mq of k minus 1. At the previous step, the input would have been mqk minus 1, in which case the output would have been mqk minus 2. So let me write that in a different color. So if we have when the input here is mqk minus 1 here, then here we will have mqk minus 2. We're just going backwards from k. So we are from the sample number k, we are going back one step, k minus 1, k minus 2, and so on. So when we go back one step here, the output here would be mqk minus 2, which is a delayed version of this. Going back one more step, the input would be mqk minus 2 and the output would be mqk minus 3, and so on. So mq of k itself can be written as mqk minus 1 plus dq of k. So we can write that relationship, but mq of k is equal to, from this diagram here, in the current sampling instant, at instant k, mq of k is mqk minus 1 plus dq of k. mq of k minus 1 plus dq of k. Now we can go back one step. mq of k minus 1 would be mq of k minus 2 plus dq of k minus 1. We are just taking k one sample time backwards. So we can write, but mq of k minus 1 is mq of k minus 2 plus dq of k minus 1. So when we go backwards one step, the input here would be k minus 1 and the output is k minus 2. So the k minus 1, mqk minus 1 is equal to mqk minus 2 plus dqk minus 1. This also has to be taken one step backward when we go back here. So I'll write again that as well in red here. So dq of k, going back one step, would be dq of k minus 1. Right? So we can write or represent mqk minus 1 as mqk minus 2 plus dqk minus 1. So therefore, we can represent this mq of k to be equal to mqk minus 1, which is this term, but this term is equal to the sum of these two. So we can write it as mq of k minus 2 plus dq of k minus 1 plus dq of k. Right? So this term here, mqk minus 2 plus dqk minus 1, is representing mqk minus 1, which is for this, plus the dq of k, we have it here. So we can again go back one more step, and likewise we can keep iterating backwards. So again I'll do one more iteration, but mq k minus 2 would be equal to mq k minus 3. So that means when we have k minus 2 here, the output would be k minus 3, and here we will have dq k minus 2. So, but mq k minus 2 is mq k minus 3 plus dq of k minus 2. So we are going to substitute this term, these two terms, the sum of these two terms in place of mqk minus 2. So therefore our m of q will now become, and that is mq of k will become mq of k equals mqk minus 2, which is equal to this term over here. So that will be mqk minus 3 plus dq k minus 2 plus, we have these terms before, so which is dq k minus 1 plus dq k. And if you see what's developing here is, we are getting a summation term of dq of k, dq k minus 1, dq k minus 2. Again we can write mq k minus 3 is mq k minus 4 plus dq k minus 3, and so on. So if we keep going backwards and backwards and backwards, we'll have a summation of all these dq terms, the delayed versions of the dq terms, dqk plus dqk minus 1 plus dqk minus 2 plus dqk minus 3, and so on. And we'll have one term of mq of k minus something, and that would be the very first term, which we will assume to be the initial condition to be equal to 0. So that would leave us with only the summation of dq terms, and that means the delta modulation receiver part can be implemented as an adder. So you see that the implementation becomes very simple in delta modulation, because all we are doing is addition or summation here. So I'm going to write down this equation again on the next page. So we have mq of k is equal to mq of k minus 3 plus dq k minus 2 plus dq k minus 1 plus dq of k, and so on. So if we keep going backwards or iterating backwards, and assuming 0 initial condition, that means if we keep going backwards, we'll have more and more terms with this dq. We'll have a dq k minus 3, a dq k minus 4, and so on, and this will keep going backwards. It will be mq of k minus some n, which we will assume to have a 0 initial condition. So that will leave us with only the summation of dq terms. So we can write this mq of k as just a summation of the dq terms, dq of k minus n, for n equal to 0 to k. So when n equal to 0, if you notice here, when we put n equal to 0 here, we'll get dq of k, which is this first term. Then n equal to 1, we'll get dq k minus 1, which is this term, plus dq k minus 2 and so on up to dq of k minus k, which is dq of 0, okay, and plus mq of k minus something, and that initial condition we will assume to be 0. So we see that the delta modulation receiver part, where we want to reconstruct mq of k, which is the quantized version of the sample m of k, is obtained by adding these dq terms. So the implementation of delta modulation is much simpler as compared to differential pulse code modulation, because in place of a predictor we have a delay, and the calculations involved are simply summation in the receiver part, because the receiver part involves or the objective at the receiver side is to get back mq of k, and we can obtain mq of k by just adding these dq terms, assuming that the initial value of mq of k is 0, right? So the delta modulation, the abbreviation for delta modulation is dm, right? So delta modulator can be implemented as an adder, or in terms of the electronic implementation we call it also as an integrator at the receiver side. So that's our first observation. And at the transmitter side, if you notice, all it is doing is it's taking a difference or subtracting the sample value and the previous sample value, right, which is obtained from the delay. So the transmitter side let me write it in a different way. Let me rephrase that sentence. At the transmitter side, delta modulation can be implemented as a subtractor or differentiator. So that reduces the implementation complexity and hence the implementation cost for a delta modulation system as compared to a differential pulse code modulation, okay? But what is not obvious from the block diagram and the discussion so far is that delta modulation is a one-bit quantizer, in the sense that irrespective of the number of quantization levels, the output produced is a single bit. It's either a 1 or a 0. So even if we have 16 quantization levels or 32 quantization levels, the number of bits per sample would not be 4 or 5, but irrespective of the number of quantization levels, the output of the delta modulator is always a single bit, which is either a 1 or a 0. So delta modulator is also called as a one-bit quantizer. So that's another next point that we are going to state. Delta modulator is a one-bit quantizer. That means it outputs only a single bit, which is either a 1 or a 0. So what that means is, unlike in DPCM, where one sample and the next successive sample can jump from the highest quantization level to the lowest quantization level or vice versa, in delta modulation, the jump has to take place one step at a time. So if the output is a 1, it will go up by one quantization step size, and if it is 0, the output will jump down by one step size. So delta modulator output can change only one step at a time. So DM output can change only one step at a time. Okay, and let me illustrate that. So what we mean by DM being a one-step quantizer is that one-bit quantizer, or it can change only one step at a time, is that suppose the first sample value is having a quantization level here. The next quantization value will have quantization value, let's say here, the quantized value of the sample is here, and the next step has to be here, the next step has to be somewhere here, and the next step here, and since it's here, and then it will go up here, and so on, right? So it can move only one step at a time. Unlike in DPCM, it is possible that we have one sample at one quantization level and the next sample at some other quantization level at a much higher level. But in delta modulation, it has to jump only one step at a time. It can jump only one step at a time. So if it's a 1, it will go up one step, so that corresponds to a 1. If it comes down, then it, as in this case here, it is going from up to down one step, so that corresponds to a 0 output. So if it's a 1, it will go up one step. If it's a 0, it will come down one step. So depending on that, the change that can happen in the delta modulator output is only one step at a time. And hence it's also called as a one-bit quantizer because it produces only one output bit each time. Now, one of the things that can happen in delta modulation is, again, when the slope of the signal is large. That means when the signal is changing very fast along in its amplitude with respect to time, right? So the slope is large. Then because the delta modulator output can jump only one step at a time, it has to jump one step at a time now. So when it is jumping one step at a time, you see that the output of the delta modulator is not able to follow the input signal that is being quantized, right? So the delta modulator output is the delta modulator itself is getting overloaded by the slope of the signal. So we call this as slope overload noise in the delta modulation. So it's nothing but it's called as slope overload in delta modulation. So let me mark that. So this part of the signal denotes slope overload in delta modulation. Okay, so that's slope overload in delta modulation. So the blue curve is the actual signal, and the red step marks are the or denotes the delta modulation output. So let me mark that. So this red steps is the DM output, and the blue signal is the actual signal. Okay, so we see that when the slope of the signal is large, then the output of delta modulator is not able to follow the signal. Ideally, it should have been following the signal as it is following here, right? If you see all of this here, it is following the signal very closely, but here it is deviating from the actual signal. So that means the delta modulator is overloaded by the slope of the input signal, which we call as slope overload in delta modulation. Another problem that can happen in delta modulation is when the slope of the signal is very small, as in this case. If you see here, the signal is more or less constant. It's not changing too much. It's almost flat, right? So that's the situation where the slope is very small, or almost zero in this case. So when the slope of the signal is large, then the output of the delta modulator is going to jump up and down between two levels. So because it can't continue going upwards because the signal is more or less flat, So the output of the delta modulator tries to follow the signal as much as possible, and in doing so it keeps oscillating between two quantization levels. So it keeps going up and down, and it basically oscillates between two quantization levels. So that's one quantization level, that's another level. So it's going from this level to the upper level, coming back to the lower level, going back to the upper level, and so on. So this property or this feature in delta modulation is called as granular noise, where it is oscillating between two levels. So, and that happens when the slope of the signal is small. So this component here, it represents granular noise. Okay, which occurs when the slope of the signal is small. So we have 2 points here. One is slope overload, and that happens when slope of input signal is large, and granular noise, which is the output of the delta modulator oscillating between two levels, that occurs when slope of input signal is small. Okay, so these are two things that can occur in delta modulation, and as far as granular noise is concerned, there's nothing we can do about it. If it is there, we live with it. But as far as slope overload is concerned, we can avoid the slope overload by increasing the sampling frequency, and we will see, just as we did in the case of differential pulse code modulation, where we derived the condition to avoid slope overload in DPCM, we will in the next lecture also derive the condition to avoid slope overload in delta modulation, and then we will compare the two conditions, that is for DPCM and DM, to avoid slope overload, and see what is the implication of both these scenarios. Okay, we'll stop here for today, and we'll continue in the next lecture.